So, here comes the question of which form of the solution to take and why. So, I wrote it as A times H0 plus B times H02, okay. And so far we have not really figured out or used the idea of boundary conditions at all, okay. So, what are the boundary conditions? Forget what's on the board. What are the boundary conditions for this problem? I have a point source sitting at the origin, alright, and radiating a field. What is the boundary condition for this problem? As the field goes far away, as I go far away, the field should go to 0. Now, when I look back at the plots that I have shown you of J0 and Y0, if I take any linear combination of J0 and Y0, will both of them go to 0 at large x? Yeah, individually each of them decays. So, both H01 and H02 seem to satisfy at least the asymptotic limit, okay. So that is not sufficient. Is there any other information that I can use physically? This will come from physics, not math. So, remember, I am at the origin over here, okay, and it is a wave equation. So, some wave is going to go out from here. That is where I have put my impulse. So, let me give you a hint. What is the time convention I have assumed throughout this thing? In the very beginning, there was remember Maxwell's equations, there was a d by dt, and I assumed a time harmonic case. I put e to the j omega t. So, that time derivative gave me a minus omega square, a j omega, and the second time a minus omega squared. But my time convention was e to the plus j omega t, okay. So, does that tell you anything? So, as to give you a hint, let us look at what happens when I go far away at very large x, okay, from the location of the point source, from the location of the impulse. If I go far away, I am giving you some extra information. I am telling you that H01 and H02, they have these what are called asymptotic forms. In general, you cannot write Hankel functions or Bessel functions in closed form. They are special functions. They do not have a closed form expression. But under some limits, very small x, very large x or whatever, they have some approximate form, and that approximate form has been written over here for large values of r or x, whatever. Okay. Now, looking at this, you get an intuition of which form is physically acceptable. Second one, because both are decaying. What is the amplitude of both of these guys? Root 2 by pi x. So, at large x, both go to 0. E power j omega t? Why does it have to counteract? It is a phasor which is constantly oscillating, but the amplitude is decaying. No problem. So, let us write this term over here on both sides. That would be the total solution in space and time, right? Remember, that is what we did with phasors. Solve it, put a e to the j omega t and take real part. Wave is going in which direction? It is going outward. Are both waves outward? Right? Only the second wave corresponds to a outgoing wave, because it is a j of x minus omega t, right? And this, on the other hand, is a incoming wave, because it is a j of x plus omega t, right. So, for that reason, because my impulse is at the origin, they can, if I am going to large x over here, this observer can't possibly observe an incoming wave like this. That is what it would mean, right. This fellow can only observe a wave that is outgoing from the origin, which is matched only by this guy, okay. So, here is so sort of a good juxtaposition of some physical intuition and mathematical formalism, right. So, based on the observer only sees outgoing wave, right. So, implies A is equal to 0, right. A is equal to 0 guarantees that the solution is purely outgoing. So, therefore, I can write that the final form is B h naught to k of r. Okay. So, we started with a general solution over here, and we said physically that A is equal to 0 is the only meaningful thing, and that gives me this. So, is my problem done? Yeah, exactly. So, I mean it's a fine, it's almost done except for the annoying factor B, which I still don't know how, what that value is, but I need to know it, because otherwise I will have that one variable everywhere. My answers will be always off by a multiplicative constant. Okay. So, what is the thing that we have been avoiding all along? R is equal to 0, right, and we have good reason to avoid R is equal to 0, because as we found out that the y, the Bessel y function, it plunges to minus infinity. But if I want to get the complete solution, there is no escape, I have to go to the origin now. Okay. So, when dealing with singularities or infinities, what is the one safe way of dealing with them? Limit is one thing. We have already seen in the 1D Green's function, when we had a delta function, did we approach it directly or did we do something else to it? We integrated, right. So, when you see a singularity, the best thing is to integrate so that you get a finite quantity, otherwise what do you do with the infinity sitting there, right.